forward. So here's an activity. So I just discussed how CP and CV for liquids and solids are very, very similar. However, I'm not going to show this derivation, at least not yet, but it can be shown that CP minus CV equals NR, or CP minus CV just equals R, which is really cool. Or another way to think of it, CPM equals R plus CVM. So spend just a moment, discussing or thinking to yourself, why is CP greater than CV? Okay, so you notice it's greater by one value of R. So it's greater by 8.314 joules per mole. So why is that? And what is the significance of that 1 unit of R? So see if you can kind of qualitatively or conceptually wrap your heads around that. Okay, so go ahead and pause the video if you need to and think that through, or I'm just going to turn to my cheater notes here so I give you the answer correctly. Okay, and so the significance, the reason for CP being greater than CV is because most systems expand when heated, particularly at constant pressure. Okay. So such systems will do work on the surroundings, right? So as something is expanding as it's being heated, it's doing work. It's doing work on its surroundings. And so therefore, some of the energy supplied as heat has to escape back out to the surroundings. And so as a result, the temperature will rise less rapidly than if it were not free to expand. Okay, so that means CP is greater than CV because if you're allowing that system to expand, you have to be pumping more heat into it to fuel that expansion. Okay, so hopefully that makes sense. So conversely, CV is less than CP, right? So I could write CVM equals CPM, of course, minus R. So CV is less than CP because when volume is being held fixed, there's no expansion work that requires an input of energy. Okay, and so what's the significance of 1 unit of R? 2 degrees of freedom. Okay, and what are those 2 degrees of freedom? Well, those 2 degrees of freedom are either changing the volume or changing the pressure, okay? Which I realize is a little bit different than the ways we talked about degrees of freedom before. And that landscape of either being able to change pressure or being able to change volume as degrees of freedom, we'll talk about that more when we discuss phase equilibria in the coming chapters, okay? And so notice that this is just for an ideal gas, right? So we'll have some other things to talk about if the gas is not ideal, and some even further things to talk about for monoatomic gases or linear gases or nonlinear gases. Okay, so this is a good relationship to know. Okay, so move.